Alrighty. We talked about last time how if we have a configuration of charges, like these three charges, they have a certain amount of potential energy. Remember, we did this with masses too. We did the exact same thing with masses, how masses that are if we have a collection of masses, they contain a certain amount of potential energy. It's all the exact same thing, except instead of being K, Q, Q over R, it was G, N, N over R. If y'all remember that from chapter 0 or whatever. So it's exactly the same. You'll probably see it on the test as well. But I do want to show you a slightly different way to think about this. And you might see this in some of the old exams, or I think maybe even in the homework I describe it in this way. But let's imagine that I have three charges. Or we'll just first start with two charges. And actually, let's first imagine that this charge is not here. And I want to ask myself the question is, how much work does it take to put this charge into its place? So for example, I have that 2 microcoulomb charge really far away, and I just want to take this 2 microcoulomb charge and move it to a position that's over here. Now what is the force acting on that charge as I move it? Like I'm just moving this charge around. What is the force acting on it? There are no other charges present. No, that's the energy.
No, you're
Oh, me. Right. Okay. Yeah. You is the variable. Not exactly. So if there are no other charges around it, what is the force required to move that charge? If it's accelerating, yeah. But if there are no other charges around it, there is no electric force acting on it. Right? Because in order to have an electric force, you have to have 2 charges. Right? Okay, so in order to take a charge, that 2 microcoulomb charge, and move it into the position right here, it requires no forces. And so in order to move that charge into that position, the work required is equal to 0. Now, I imagine this charge. Now, I have this 2 microcoulomb charge in place, and now I have this second charge, and I want to put it into this position. So imagine that I have this 3 microcoulomb charge over here, an infinite distance away, where the potential at an R equal to infinity is what? It's equal to 0. That's our reference point. When R is really big, V goes to 0. Remember, V, our voltage, our potential, is energy per unit charge. So imagine I have this negative 3 microcoulomb charge over here. I want to determine how much work it takes to move it from over here where the potential is 0 to over here where the potential at this point is equal to K times this Q divided by R. Now, I've already said that my work is equal to Q delta V. All right, so the work required, I'll call this Q1 and I'll call this Q2. The work required to move particle 2 into position is going to be Q2 times delta V due to particle 1. And the way that works out is that work 2 is going to be Q2 times K Q1 over R minus 0. This is my V initial. This is my V final. Because I'm moving it from my reference point way over there at R equal to infinity to this position where I'm at distance R from this charge. But if you notice, this is the same thing. K, Q1, Q2 over R. That's the same thing that we said over here. So the work required to assemble these charges is equal to the potential energy of the charges. We've seen that before in work energy theorem, that if I do work on a system, then I change its energy. All right. So we can think about the amount of potential energy in a slightly different way in thinking about what is the work required to assemble that. Just wanted to point that out because on the homework and also in some of the old tests, you'll see it explained in this way. But it's exactly the same as saying what is the potential energy. And then further, if we had a third charge, say I had a Q3 right here, and I want to know what is the work required to bring that charge into place, that's going to be, get rid of this right here. That work required to bring Q3 into place will equal to Q3 times the potential due to charge 1 plus the potential due to charge 2. Because now, when I'm moving this third charge into place, over here, at an infinite distance away, I have 0 potential. But as I move it up into place, I'm moving it into a potential that's affected by both of these charges. So this would look like our work 3 would be K Q1 Q3 over R plus K Q2 Q3 over R, where R is this distance here, assuming that it's all 1 meter. So our total potential energy will equal to this potential energy plus this potential energy plus this potential energy, or the total amount of work is equal to those 3 terms. But remember, if I have 3 masses, or excuse me, 3 charges, then the total potential energy is the potential energy due to this pair plus this pair plus this pair. That's where we left off last time, where if we have more than 2 charges, or if we have more than 1 charge, the potential energy is the potential energy due to any one combination of 2 of those charges. All right, so just remember that our work and our potential energy are basically the same by that work energy theorem. If I do work on a system, I change its energy, and you can think about determining the potential energy of a configuration of charges. You can think about it in this terms of work. What is the work required to assemble those charges? Or you can think about it in terms of, once I have them assembled, what is the potential energy in that configuration? I think the latter is probably a little more straightforward and easier. That is just calculating what is the potential energy of this configuration. But we'll see on the concept test that there's some questions about the work required to assemble these charges. Let's try this quick test. So let's consider this. I have Q is 1 coulomb. So just to be clear, that means this is 1 coulomb, this is 2 coulombs, and this is 4 coulombs. It's 1 times 1, 2 times 1, 4 times 1. I want to know how much work is required to configure this set of 3 charges. I'll work that. I'll be right back. What is the work required? Remember, work and potential energy, those are the same, so you can also replace that work. guys. I'll be right back. Go ahead and finish this up as soon as I come back. Take about 15 more seconds. Ask your neighbor if you're not sure. Looks like most of you have it right. I'm going to stop at 4 minutes. Okay. 4 minutes? Okay, yeah, I think A is right now, so let's double check. Remember, this is just like we did before in chapter 0 when we were doing masses, except it's just charges. So first thing I want to do is find the potential energy due to these two charges. That's going to be 9 times 10 to the 9th, Q over R, 1, 4 over 2. That's 18 times 10 to the 9th. And then I find the potential energy for these two charges, 9 times 10 to the 9th. 1 coulomb, 2 coulombs divided by 2 meters. That's 9 times 10 to the 9th. And then find the potential due to these two charges. That's going to be 9 times 10 to the 9th. 2 coulombs, 4 coulombs divided by 2. That is 36 times 10 to the 9th. And you just add those up. 36 and 27, what's that? Is it 63? Yeah. Is it 8? 8 was right? Yeah. Okay, so I just add these three quantities up, and I get the total energy, or the total amount of work required to assemble those charges. Both of those are correct. All right. There's a homework question like this, but again, it's just like what we did in chapter 0 on masses, gravitational energy of masses. All right, let's look at equipotential lines. Y'all did this back in lab 1, I think, or lab 2. But an equipotential line, in fact, I think we did this in chapter 0 when we were doing gravitational fields, but we see it again because electric fields are very similar to gravitational fields, which is the whole reason we did gravitational fields. An equipotential line, or a surface, it can be a surface, in fact, if you're looking at it in 3 dimensions, is a line where the potential is the same or equal. Along these lines, the change in potential is 0. Delta V equals 0. And also, because of that, because our change in potential is 0, remember, potential is energy per charge. So as you move along these lines, the potential, the energy doesn't change, because the energy per unit charge doesn't change. And so the work required to move a charge along a potential line, an equipotential line, is equal to 0. If you remember delta V, this is equal to delta, or VB, or V final minus V initial, I'll just call it VB minus VA. And so this is equal to our delta PE over Q. So if along a potential line, an equipotential line, these two are identical, delta V is equal to 0, that means that my potential energy isn't going to change. And if my potential energy doesn't change, that means that the work required to move a charge along that line is equal to 0. your electric field and your equipotential lines will always be perpendicular to one another. So if I draw my equipotential lines, it'll look like that. So you can imagine that if I have a charge, say a plus Q charge, I can move along this line with no change in energy and no work required. That should make sense to you because remember the force, the electric force that is acting on this object is in this direction. And so if I'm moving perpendicular to that force, then it's not going to change the energy and it's not going to require any work because I don't have to exert any force to move it along that path. In a similar way, whether the electric field is into or out of the charge, your equipotential line will still be perpendicular. And you can have numerous equipotential lines. I mean, in reality, you have an infinite number of equipotential lines. It's, like a topographical map, for example, where you have these lines that represent certain elevations. These are lines just like on a topographical map, but they represent different potentials. So for example, if I have on this one with the positive charge, I have different equipotential lines. This one might have V equal to, say, 8 volts. This one be V equal, would it be bigger or smaller as I move further away? It's going to be smaller, right? So it's going to be, say, 6 volts. And on, just like a topographical map, where the line shows a certain elevation as on a topographical map, or in this case, a potential. If I have a system like this, and I draw my equipotential lines, you just draw them perpendicular. So that would start out like this, so that it's perpendicular. Notice it's perpendicular. I'll keep going like that. And y'all did this in lab where you marked out the equipotential lines. You actually took a voltmeter, which is potential, and you put your lead here, and then you grounded the other lead, I think, and measured the potential and marked out where that potential was equal to remain constant. You can keep drawing them, something like that. Down the middle, it's just going to be a straight line, looks sort of like a basketball court. And then over here, all right, so just to give you some reference here, say my potential here would be 10 volts. My potential here would be 5 volts. My potential here would be, what would it be right down the middle? It would be 0. You can think about this because, say at a point here, my distance from here to there and my distance from here to here are the same. But because this is a dipole where I have equal but opposite charges, the potential, say at this point, or any point along that line, are equal distances to those two charges, and so V at that point will equal to K times plus Q over R plus K times minus Q over R. Because R is the same, that's going to add up to equal to 0. And that will be the case anywhere along that line down the middle. So that would be V equals 0 volts. Here I'd have V equal negative 5 volts, and here I'd have V equal negative 10 volts. You can measure these equipotential lines just with a voltmeter, like y'all did in lab. All right, let's try this little quick test. What points is the potential at its greatest value? What point or points is the potential at its greatest value? Alrighty, let's see, I'll stop at 35. Very good, E is right. These two have an equal potential, and because they're closer to the charge than any of the other positions, they have the larger potential. All right. That wasn't quite 90%, but I'll give you a joke. Yeah. What did the dog say after a long day at work? Rough. That's the way I feel now. I don't know about y'all. Okay, one more thing in this chapter. Y'all haven't done partial derivatives, but you really know how to do partial derivatives. It's not that hard. But we'll see that there's a relationship between the electric field and the potential that is the partial derivative of that potential. So the greater the change in the potential, the potential, not the voltage, or voltage and potential are sort of interchangeable. The greater the change in the potential, remember that's energy per charge, the charge will experience a greater work due to the E field. So our change in potential is related to the electric field. If I have a greater change in potential, then that means that I'll have a bigger electric field at that point. So for example here, again, imagine that this is a topographical map. Let's say that this is V equal 1, V equal 4, this is V equals 6, and this is V equals 7. Like a topographical map, notice that these two field lines, or excuse me, these two equal potential lines are farther apart. And so it's like they represent potential that's farther apart. And here, where they're closer together, and it goes from 6 volts to 7 volts, whereas here it goes from 1 volt to 4 volts. Y'all follow what I mean? It's like a topographical map. When our field lines, excuse me, when our equal potential lines are farther apart, they represent a greater gulf in the potential, or a greater difference in the potential. And similarly, I show the electric fields here. When my, I'm sorry, this should be separate. I have these backwards, I'm sorry. When my potential is a bigger difference, I should have a big electric field, and when it's a smaller difference, I have a smaller electric field. Sorry about that. So here, I have a small E field, and here, I have a big E field. When my potential changes a lot, all right, when there's a big change in the potential, that means I have a bigger electric field. That should sort of make sense to you, because if I have a big change in potential, what's that saying? Well, that's saying that I have a big difference in the amount of energy per unit charge. And if I have a big difference in the amount of energy per unit charge, that means that I must have greater forces acting, and so I must have a greater electric field. Yeah, Cody?
All your volts go the other way, like wouldn't it start being smaller at the outside?
You're right. Yeah, I'm sorry. So it should really be, what? Okay, like 7, 1. Y'all see what he's saying? Yeah. Okay? Yes. All right. So when the potential changes a lot, the E field is bigger. That is to say that the electric field is proportional to a change in our voltage, or delta V, or difference in potential. If this is big, that means this is big. And I want you to remember that when I say a change in something, this delta, a change in something, this is really should set off some alarm bells that we're talking about a derivative. Because derivatives at their their root function is to talk about how things change. That's why we use them a lot in kinematics, because we're talking about how things are changing with respect to time. A derivative does describe how something changes. All right, so it's a quick little derivation. Don't worry too much about this derivation, but just for those of you that are interested, our work, well, I know all of you are interested, but you're not going to have to do this derivation on the test, is what I'm saying. The work is equal to negative Q times dV, and our work is also equal to F dot D. our force dotted, our dot product of the force and displacement. So we can set these two equal. I can say that negative q dv is equal to F dot d. And remember, F dot d is equal to F cosine of theta. And I'm going to change that d to a ds. So this is sort of our generic distance, our displacement. But I'm going to change it into this, into a differential element where I'm going to change the d to an s and just take the derivative of it. So I'm just translating this into a differential element. So negative f, or f cosine ds, and then I have this negative q dv. And further, I can say that this f right here becomes q times e, because f is equal to qe, cosine theta ds. All right, and here, as I said, ds is the differential displacement vector. It's that differential element in our displacement, and it is a vector quantity in the direction of the E field. And E cosine theta is the component of the electric field that's in the same direction as ds. So I have this E cosine theta and ds. Those are both in the same direction. Remember, that's what a dot product does, is it takes one vector and it finds the component of that vector that's in the same direction as the other vector. So that's why we use it in work, because we want to do that when we're calculating work. Find the force and displacement that are in the same direction. Okay, so that's a lot to say in order to come up with this expression, that ES, that is the electric field in the direction of that vector, ds, is equal to negative dv ds. All right, to say this more correctly, we would express it in terms of a partial derivative. In a partial derivative, instead of writing the d, we're going to use the Greek letter del, the lowercase d letter del, or delta, but we often call it just del. And it's going to look like this. E in the x direction is going to be the partial derivative of v with respect to x. So this symbol right here, this is the lower, or we call this symbol just del. It's not lowercase, delta. Delta looks different. Isn't that right? That's capital delta. Yeah. Y'all do partial derivatives in Calc 3?
Yeah, that's how they call it in Calc 3.
Okay. It's sort of like a Greek letter delta. EY is going to be negative del V del Y, and then EZ is going to be negative del V del Z. Don't worry, I'm going to show you how to do this. It's not much different from a regular derivative. It's just that when you have an equation with multiple variables in it, say x, y, and z, if I take the partial with respect to x, I treat y and z like they're constants. So I just treat those like numbers. So you'll find that partial derivatives are just like derivatives. They're very similar. But you just sort of have to treat those extra variables as constants. And then the total electric field will equal to Ex in the I direction plus Ey in the J direction plus Ez in the K direction. Because you find the components of the electric field vector by calculating the partial derivative of that potential function with respect to the various x, y, and z variables. So for example, let me do a quick example and then I'll let you do one on your own. Let's say that I have a potential function. I'm just going to do it in terms of x and y. And I don't know, let's say that it's 3x squared y minus, this is, 3x squared y minus 4y squared. And I want to know what is the electric field at a certain position, let's say x equal 1, y equal 2. Probably see a test on the question on the test like this, where I just give you a potential function and I ask you what is the electric field. Once you do it a couple times, it's not that hard, especially if you know how to do derivatives. So remember, guys, that if I want to take the derivative, say for example, the derivative d dx of, say, I don't know, x cubed, I say 3 times x to the 3 minus 1. So if I have, say, px to the a, and I want to know the derivative of this with respect to x, it's going to be apx to the a minus 1. Okay? If you're a little shaky on your derivatives, just come see me. We're just going to do these exponents. It's not so these polynomials like this. So, all right. So if I want to know my electric field, I say Ex is negative del V del X. That's going to be negative of the partial derivative of this function with respect to x. So what that means is I'm going to treat y as a constant. So I'll treat it in the same way that I treat the 3. So I'll do this first one and let y'all do the next ones. It's going to be negative 3y, and then the derivative of x squared is 2x. And then the next one, del v del x, is just going to be 0, plus 0, because the derivative of this with respect to x, that's just a constant, and the derivative of a constant is 0 because it doesn't change. So this is going to be equal to negative 6xy. And then if I want to find ey, it's going to be negative del v del y, which is just going to be 3x squared, that's for this term, minus 8y. So now if I want to know the electric field at x equal 1, x equal 2, I just plug in those values. So x equal 1, x equal 2, that'll be negative 6 times 1 times 2, which is negative 12. And this will be 3 minus 16, which is negative 13. And so my electric field here is going to be negative 12I minus 13J. That's in volts per meter or newtons per coulomb, depending on the units. Yeah, Cody? Oh, yeah, you're right. So this should actually be, what was the function? Yeah, this should be a positive right here. Positive, positive 19. Thank you. Okay, let's try one. You have one in the homework, but let's try one. This is pretty powerful because if you have a known potential field like you have here, then you can calculate what is the electric field with this partial derivative at any point in space. And it's pretty simple to set up these known potential fields in the lab, or if you have a collection of charges, you can calculate what the potential field is. And then it becomes really simple to find the electric field. All right, so consider this function. Just want to know what is the electric field due to this function, xy squared minus 3yx plus 4y. And then what is the magnitude? Actually, let's just find the magnitude of the force. Oh no, you can do the magnitude in this. Let's just do the force in vector notation. On the electron due to this electric field. So remember, the electric field in some direction S is equal to negative del V del S. So I need to do that for X, Y, and Z. Then you plug in your coordinates for X, Y, and Z, and you get your X, Y, and Z components of the electric field. And then to find the force, you need to remember that F is equal to Q times E. Give you a few minutes to head start. These are functions I get. Is this what y'all got as well?
Yeah, it's a distribution thing.
Yeah, I have a negative in front of both of them. Sorry about that. So I have a negative here and a negative here. Right. And then, so I can just put in my values for x equal 1 and y equal 1. So this is going to be negative of 1 minus 3, which is what? Positive 2. And then over here, I get negative 2 minus 3 plus 4. Negative 1 plus 4, so just negative 3. So at that point, x equal 1, y equal 1, the electric field is equal to 2I minus 3J. That's in newtons per coulomb or volts per meter. Okay, and then this adds a further question. What is the vector notation of the force on the electron? Remember, F is equal to QE. So if I wanted to find the force, what would I do? Okay, I'm just going to multiply it by Q, right? The charge of my electron is negative 1.6 times 10 to the minus 19 times 2I minus 3J. And so it's going to be negative 3.2 times 10 to the minus 19 I plus 4.8 times 10 to the minus 19 J, and that's in newtons. And then you could go further and find the magnitude and direction. But so we did electric fields on the last test, right? Yeah. So you won't. I'm not going to do any vectors on this test. Okay. So you'll probably see, give you a potential field, ask you what is the electric field due to that. Okay. I had a thought this morning. You know, I said we'd do that derivation for the potential due to a line of charge. I had a thought that maybe we would do it at a different time other than the exam. Like maybe in the last 15 minutes of class one day, you would just do that and you'd go ahead and turn it in. I'll announce it, of course, several days in advance. And that way, you have a little extra time in the exam. I wouldn't add extra questions by pulling that one out, but you would have a slightly shorter exam, but you'd do part of it ahead of time. Would y'all like that? Yeah. You'd have to memorize that derivation, but you know, I understand that a lot of you are just going to memorize it and then dump it right afterwards, but I do find that memorizing things does help you to sort of understand them better. So I think that we'll probably do that. Our exam is coming up that Friday, so I think that we'll probably do that that Wednesday beforehand. But I'll announce it well ahead of time and and show you exactly what to expect. I think that might work well. All right. The exam is 2 weeks from today? Yeah, 2 weeks from today.
If it, do it on Monday morning.
Why Monday?
Because you have the weekend.
Oh, after the exam.
No, before or after the 11th.
Okay, we'll see. I'll think about it this week.
Yeah,
I don't really care.
It's a study in the year.
Okay, we'll see. All right. Okay, let's have a few clicker questions regarding this stuff, and then we'll move on into capacitance. You've done all these, right? I think we left off on this one. Am I right about that? 2.2? All right. So which group of charges took more work to bring together from a very large initial distance apart? Was it group number 1 or A, group number 2 for B, or group number 3 for C? Which required more work to bring together? Or you can think about them, which has the most potential energy contained? Both of those questions would be the same. The work required to assemble the charges is equal to the potential energy in the charges, in the configuration of charges. Remember, our potential energy is KQQ over R. Right. 10 or 15 more seconds. Stop at 1:15, let's say. Okay, good. B is right. The thing about this, it seems like they should have the same energy, but it's not. Let's just take a look. If I consider these charges, it's going to be K2, 1 over D. So this is going to be like 2K over D is the potential energy. But over here, I have this configuration, which is going to be K1, 1 over D. This configuration, which is the same, and then this configuration, which is also the same. So the total potential energy is going to be that times 3, or 3K over D. So this is bigger than this, so it takes more energy to assemble these 3 smaller charges than it does to assemble the 2 and the 1 Coulomb charge. So B is the right answer there. Where is the electric, or what is the electric potential at point A? I have 2 charges, a plus 50 and a minus 50. And this point A is 60 centimeters from the minus 50, 30 from the plus 50. What is the potential there? Is it greater than 0, equal to 0, or is it less than 0? Stopping at 50. Just 5 more seconds. Okay, awesome. A is right. Because I'm closer to that positive charge, remember when I'm adding up potentials, it's KQ over R plus KQ over R. Because I'm closer to this positive charge right here, then the positive voltage is gonna overwhelm the negative voltage. I'm further away from the negative charge, and so the potential due to it will be smaller. It'll be negative and smaller in magnitude. So I'll have a net potential that's 0. I mean that's greater than 0. What is the electric potential at point B? So now at point B, I'm along the origin here, I'm along the y-axis, so I'm equidistant between these 2 charges. What is the potential at that point? I'll stop at 38. 38. Okay, good. B is the right answer. We saw this before, but when I'm equidistant, I get a positive V here, I get a negative V here. They add up to give me equal to 0. My potential is 0. 4-point charges are arranged corners of a square. Find the electric field and the potential at the center of the square. We had a very similar question before, but here I want to know, is the electric field 0 or not 0? Remember, put your positive test charge here. Ask yourself the direction of the electric field. And then is the potential 0 or not 0? All right, I'll stop at 55. 55. Oh boy, okay. All right, so first of all, the potential, hopefully that should be the simplest part. What is the potential? if I have equal numbers of positive and negative charges, my potential is going to be 0, as long as I'm equidistant from all of those charges, which in this case, I am the same distance from all 4 charges. I have 2 positive charges, 2 negative charges, so the voltage of the positives and negatives will cancel out. So the potential is 0, so it gets rid of those, B and C. And then I want to ask myself about the electric field. Well, the electric field due to this charge is in this direction. The electric field due to this charge is in this direction. The electric field due to this charge is in this direction. And the electric field due to this charge is in this direction. 0 electric field or not 0? Not 0, right. So D is the right answer. Listen, you will have potential stuff in the multiple choice, but because we've already done electric fields, you won't see a lot of this stuff with the electric fields on the test. You'll see electric fields in the terms of like the partial derivatives that we just did, but these sort of conceptual questions you won't see regarding electric fields. But you could see questions regarding the potentials. At what point is V equal to 0? 1, 2, 3, 4, or A, B, C, D, or is it E, all of them? Let's stop at 25. 25. Okay, good. E is the right answer. Why did the son not go to college?
It says already right.
No, that's not my punchline. You should never give your own punchline when somebody tells a joke. It's kind of rude, Desiree. Because it's got like 1,000,000 degrees. But yours is a good punchline. So I like it. Okay. Which of these configurations gives V equals 0 at all points on the x-axis? So I want points along the x-axis where I'm equidistant from pairs of positive and pairs of negative charges. All right, we'll stop at, say, 55, 55. Just guess if you're not sure. I'm doing pretty well on that extra. All right, A is right. So you want to find points along here where I'm equidistant from the positive charge and the negative charge so that the potential equals 0. Similarly, here and here, potential due to those cancel out. But if I look over here, say if I take a point on that x-axis, those potentials don't cancel out because I'm not equidistant from those charges. So, for example, here, just considering the plus and the minus 2 microcoulomb charges, the potential here due to those 2 charges would be more positive than negative because I'm closer to the positive charge. And so when I add up the potentials, they'll give me a net positive potential. Likewise for C, you get the same thing. Here, I'm just going to give you the answer, but it's along the y-axis. So the same thing along the y-axis. Here, along the y-axis, I'm not equidistant from those 2 charges, so I don't get a cancellation, so it's not A. Here, doesn't work there either. But over here, I am equidistant from these charges, so the answer is C. Then I get, along the y-axis, I get V equals 0 for option C, but not A or B. Which 2 points have the same potential? Sorry, can y'all see that? Yeah, you can see it. Which 2 points have the same potential? I'll stop at 30 seconds. We'll make this our last question. Okay, awesome. D is the right answer. C and E, those are equidistant from the charge, and so they have the same potential. And I was thinking about this the other day. You ever think about why, whenever you're looking for something that you've lost, that you always find it in the last place you look? Right. Alright, listen, we're going to start on circuits next week, so make sure you got potential and all this jazz down before we move into circuits, because it's going to be quite a bit different from what we've been doing. So now's a good time to sort of step back and make sure you got potential fields and electric fields and stuff. Have a good weekend.